Okay, so now let's, for this hour and then next week, we're going to talk a bit about training networks. And we'll start with the loss functions that we're going to choose and this maximum likelihood estimation. And then I'm going to talk a bit about the exercises for today. So the idea is that we start this part of the subject matter, how to train the network. You get a feeling for how the things behave in these two examples. And then next week we continue this and some ideas of how to initialize the weights, how to check whether convergence is good, and then regularization and so forth for next week. So let's start with the loss functions. The basic concepts here, we have some labeled data. So we have the features and the target values that we want. In regression, target values would be a continuous range that we want to approximate. In classification, the target values would be the class label. And there, we suppose there is some function in the universe, in abstract, that makes the target values a function of the features. So we suppose that there are some relations between the two of them. What we want to do is, given a sample of examples, we want to find the best parameters to approximate this hypothetical function. So the question is, suppose that we have a linear regression, we have these coefficients for the linear combination, and the question is how we find the best parameters. What is the measure that allows us to find the best parameters? So if we have these data points here in red, we could try to fit many lines into these data points. We have an intuition that some of these are bad fits. For example, this green line doesn't seem to go near the points at all. Some may be a bit better, or maybe the points are not really in a straight line, so maybe we should not use a straight line. So we have some basic intuition about this, but we cannot really train our model with just our intuition. We need to quantify this in some way. So what we're going to do here, we have some assumptions about the probability of having those kinds of values if we have some models about that probability. So, for example, let us suppose that the values that we have here, the y values that we have here in the vertical axis, were measured as some function that we don't know of x, plus an error, say, in our observations or in our measurements to obtain those values. We want to approximate this function f with our own function, because we don't know what f is like, but we can create a function, for example, a straight line. Let's suppose that f is like a straight line. And we also have parameters, so we need to decide what's the slope of the line, where the line is. But the idea is that we're going to use this function with parameters that we're going to fine-tune, where we can input x, and the output would be the same as this unknown function f that we're trying to approximate. So if we assume that this error is normally distributed with a mean of 0 and some standard deviation, and if we assume that we have our parameters right, so our function g is close to f, then the probability of the y value coming out at some point given the value of x should be some normal curve around what we predict from our function adjusted with the parameters plus this error with this standard deviation. And we can figure out this from some distribution. Our data set, so we obtain a sample from some distribution, and we can try to compute the probability of having those combinations of x and y, so the probability of obtaining that data if we assume our model is correct. Note that we cannot compute the probability of having that data without assuming anything, because now we don't have a way of computing. So if I ask you what is the probability of the coin falling heads, if you don't assume anything about the coin, you cannot compute the probability. So what you can do is you will assume, for example, that the coin is well balanced, the probability is 50%, and then you check what are the odds, for example, of coming heads 10 times in a row. And then you maybe suspect that the coin is not balanced or something like that. But you need to work things backwards. So first you assume a model, you compute the probability from the model, and then you check if this probability makes has a high probability for the data, that is, your model is likely to be true. So this is the idea of likelihood. We can compute the probability of our data, these pairs of x and y values, from our model, and this is the likelihood of the model. A model is more likely if it tells us that the data is more probable. The model is less likely if it tells us that the data is improbable. Note that we cannot, in this sense of probability, we cannot really talk about the probability of the model, because if we consider probability in the frequency meaning, that is, the probability of an event is the frequency of that event over infinite trials, then we cannot really talk about the probability of our model or our parameters, because those are not random events. It's something that we're choosing. So they would always be the same if we randomize things. There is a different approach, which is Bayesian probabilities, where probability is about uncertainty and not about randomness, and that gives us a different approach altogether. We're not going to talk about that. But for this one, what we can talk about the model is the likelihood. So the likelihood of the model is the probability that we draw a random sample of data, and it comes out as it did in our case. And this is computed according to the parameters and the model that we have. So we want to find the parameters that make the data most probable according to what the model is telling us. And this would be maximum likelihood. That is, we want to maximize the likelihood of the parameters. So the likelihood of the parameters given this data set that we have is the joint probability distribution of the data as computed by our model. So given what we assume about the data. And we can decompose this into the conditional probability of the values we're trying to predict given the features, and the probability of the features coming out that way. So one thing to do usually here when we're trying to maximize these probabilities is to get rid of all these multiplications, because they can be messy for computing things. So we use the logarithm. The value that maximizes these products is also the value that maximizes the logarithm. And we can ignore this probability of the features because that has no relation on our model. It's independent of the parameters we're using to try to predict the y values. So the parameters that maximize this expression will be the same that maximize this one, because this part has nothing to do with the parameters. Remember that the probability of y given x, we have to estimate that from our model with the parameters that we give it. The probability of x, we don't estimate that because it doesn't have anything to do with our parameters. So this would be the solution for the maximum likelihood on our regression here. And we can now replace here, this is a general expression for any model, but our particular case, we are assuming that we have this function that approximates f, and then there is this normally distributed error around the function. If we use the expression for this Gaussian distribution with the sigma, we get this expression here. This is our function of the parameters, and this is a consequence of that random error. And when we solve that with the logarithm, we get this. So we want to maximize this expression here, minus the sum of the square of the differences between the values that we observe and the values that we predict. So maximizing the negative of this is the same as minimizing this. So we change the sign, and this is basically minimizing the quadratic error. So the reason why for a regression in this case, a linear regression, but we can generalize, we are minimizing the quadratic error, is because we are assuming that we are approximating the target function. We have a random error around the values that we measure. This is normally distributed, and we want the maximum likelihood solution. That, when we do the calculations, comes down to the quadratic error, the sum of the square errors. Or if we want, we can do the average, the mean square errors. Sometimes it's 1/2 the square errors. You can usually find this like this, because when you compute the derivative of these two will cancel out with that one and give you a simple expression. And it makes no difference because we want the minimum, the parameters that minimize the function. So any rescaling will give us the same result. So the main message here is that when you're doing a regression, you're minimizing the quadratic error because you're assuming there is a normally distributed noise error around the predictions that you have, and you want to find the function that maximizes the probability of the data being what it is. So maximize the likelihood of your parameters. Now, once we have this, we can do the gradient descent thing. So we have this loss function. We start at one point, we compute the gradients, we slide down the function, and we do this repeatedly until we get the minimum value. So, how can we generalize this for other problems that are not just regression? We saw this for the simple case of a regression. Now let's see when we do a maximum likelihood estimation of our parameters, what happens in general. So let's ignore the problem of trying to predict something for a moment and generalize this, and consider that we simply have a set of data, let's call everything X, that we drew at random from some population. There is some probability distribution for these values. So if for example, you go somewhere and measure the heights of penguins or the length of swordfish or something like that, these different measurements have different distributions because of the way those aspects that you're trying to measure work in reality. We don't know exactly what this probability distribution is, but the idea is that we have a sample from that probability distribution. Now, we can have our own models, and we can compute probability distributions from the model. So if we have some, for example, a straight line with a normal error or something like that, we can, depending on the parameters, compute the probability of the data coming out that way. So remember that our models, when we instantiate them with parameters and obtain specific hypotheses, can give us an idea of what the data should be if the model is correct and if those parameters are correct. So if the hypothesis itself is right. So what we want to do with maximizing the likelihood is maximizing the probability that our model predicts for that specific data that we have. So if we have, for example, a hypothesis that tells us that penguins are on average 2 kilometers high and vary about 10 meters to either side, then we compute the probability of penguins that we measure, and it's very low, and we can reject that model because that's probably wrong. On the other hand, if the probability of the penguins we measured is high according to our model, then the model is more likely. So basically, this is what we want to do. We want to find the parameters that maximize the probability of the data that we have according to our model using those parameters. This is maximum likelihood. But now let's look at this in a slightly different way, because doing all these products can be very bad. You can have underflow and so forth, and it's easier to just sum the logarithm. So this is basically the same thing. Maximizing this product of the probabilities for all the data that we have is the same as maximizing the sum of the logarithms of the probabilities for all the penguins, for all the fish, or whatever. But the value for our parameters that maximizes this sum is also the value of our parameters that maximizes the average value of the logarithms. We are simply scaling everything, but the maximum is the same. So we can replace that sum with an average, an expected value. This means that we want to find those parameters that, on average, predict the highest probability or the highest logarithm of the probability for each data point that we have. This is the same as maximizing the sum, we're just maximizing the average. Okay, so this is maximum likelihood. We can convert everything into this expression. Maximize the average probability estimated by our model for all the data points that we obtain. Now, let's consider a different question here, which is the difference between probability distributions. So you can measure this. This is an information theory concept. This Kullback-Leibler divergence measures the difference or the divergence between probability distributions. And what it is you can have the probability for the data that we have. This is some probability distribution and the model, and we are computing the average according to the probability distribution of the data of the logarithm probabilities of each of the any point, and minus the logarithm of the probabilities of the other distribution, in this case the model. So basically, if those two are the same, then the distributions are the same, and that divergence falls down to zero. The greater the difference between the different probability distributions, the larger this divergence will be. Now, if we are trying to minimize according to parameters of our model, and this the probability of the data itself does not depend on the parameters of our model, because this is just the data that we have. We can ignore that part. The value of our parameters that obtains the maximum or the minimum value will be the same, and we can consider only this part. So if we consider a minimization of this minus the logarithm of the probabilities given by our model, and what on average happens when we apply that to the data that we have, we see that this is the same as maximizing the logarithm of the probabilities of our model. Because again, we have this minus here, like happens in the linear regression, for the minimization, and it's the equivalent of the maximizing without the minus sign. So this is what we had for maximum likelihood, and this is basically the minimizing the divergence between the two probability distributions. So one way of understanding what we want to do here is that we want to set the parameters of our model in such a way that the probability distribution that our model is giving us is as close as possible to how the data is distributed in the sample that we have. So we're trying to match the two probability distributions. We're trying to reduce the divergence between them. And this is what happens when we're trying to do maximum likelihood. So this is essentially what we have here, the expected log probability of one probability distribution assuming the other. This is the cross entropy measure in information theory. So this is the logarithm of the probability according to one distribution. When the data is distributed, it comes from the other distribution. And this, even though cross entropy usually is, sometimes it's used to refer to specific things like logistic regression and so on, it's actually a more general concept because it applies every time you're trying to match the two probability distributions. You're trying to minimize the cross entropy between them. So, in general, what we're doing here is minimizing the cross entropy between the distribution of our data and the distribution of probabilities that our model is giving. Now, this is what we're going to use to compute the loss function. The thing is that the actual function that we have, even though we're always doing maximum likelihood, so we are always doing cross entropy and minimizing cross entropy, the actual function that we have depends on the model, because now it depends on what we are assuming in detail about the parameters and the probability distributions and so forth. So this would be a generic thing for supervised learning, where we can split this X. This X is just the data in abstract, but we can split it into two components. The thing that we use as input and has nothing to do with our parameters, and the output we're trying to predict from our parameters and the input and its conditions on that input. So for the specific problem of supervised learning, we're actually trying to match the probability distribution of the predicted values, the epsilon that our model is giving, to the distribution in our data set for those values. The X we can ignore because we're not trying to predict those, and the X has nothing to do with our parameters. But for the general case, you just consider the distributional probability of the data. Now, what happens when we do this? Find the loss function by this cross entropy for linear regression is what we saw before, and we get the quadratic error. So minimizing the cross entropy between the predicted values of our models, how they're distributed, and their distribution in the data, in the case of regression using those assumptions on the error, will end up being minimizing the quadratic error. But now we can use this for other cases. So I'm not going to do the demonstration here, but if we use a sigmoid function to predict the probability in a binary classification, then we want to maximize this probability, so the likelihood of our parameters will be the probability of the data, and basically this is the probability when we predict the probability we assign to belonging to class 1 when the example belongs to class 1, so this is raised to 1, will have its own value. If the example belongs to class 0, this will be just 1, so it won't change anything. And this is the opposite case, the probability we assign of belonging to class 1 when the example belongs to class 0. That should be a small value so that we get a large complementary value, the complement value here, and then the same thing, same operation there, put it at 1 or not, depending on whether that's the class. But when we do the logarithms and so on, we get this logistic loss function that is adequate for the sigmoid output. So remember, we use least mean squares or minimizing the quadratic error when we're doing the regression. But if we are trying to predict the probabilities with the sigmoid activation, then our model is different, and the same approach, the same cross-entropy minimization, brings us to a different loss function. And the same thing goes when we're doing, for example, multi-class classification, where we have this softmax function, and then we have the softmax cross-entropy, which is a different function. So the idea here is there are other approaches, because remember that we are assuming that probability is frequency of random events over infinite trials. If we assume that probability is uncertainty, in that case we can consider probability distributions for the parameters and so forth, and that's the Bayesian approach. It has a different result. And there are some approximations like maximum a posteriori and so on, because the Bayesian approach is computationally a lot more demanding. But I'm just talking about maximizing likelihoods, so this basic idea. So this means basically adjusting the probabilities that our model predicts to be as close as possible to the probability distribution of the data that we have. And even though the approach is always the same, depending on the model, the loss function will be different. So if you're using, for example, sigmoid activation to classify in a binary classification problem, you should use that sigmoid cross entropy. And now here comes a more implementation detail. When you're actually trying to minimize this with the numerical methods, numerical stability is very important. So you should, if you're trying to predict from your neural network, then at the end of the network you should have the sigmoid activation, and that tells you the probability. But when you're trying to minimize the error and adjust the parameters, you should not be using the sigmoid activation and feed the linear part of the neuron directly into this loss function sigmoid cross entropy, because this one will then compute the the sigmoid internally, but in a way that is optimized to avoid numerical instability and so on, and so it works better with the minimizers. If you put the sigmoid there and then compute yourself the logistic loss, for example, then things will not work well. So remember that this one inputs what is in this context called the logit. The logit function is the inverse of the sigmoid, but in this context we are calling the logit what goes into the sigmoids to get the result. So the logit would be this part here, which is the linear output from the neuron. Okay? So remember, when you're doing this sigmoid cross entropy, feed it the linear part of the neuron before using the sigmoid activation. So basically, when you're doing this in TensorFlow, you have two different operations. You have the neuron with the linear part and then feeding into the loss function for the optimizer, and then the linear part of the neuron feeding into the sigmoid function for prediction. So when you're training, you're using one of the branches. When you're classifying your data, you use the other. Okay? The same thing for the softmax cross entropy. You're also feeding in the linear activation of all the neurons, and the softmax loss function will be computed here in this softmax cross entropy, also because of numerical stability on the sigmoid. Then when you're going to do the classification, you just use the softmax activation to classify. But you're going to do this in the tutorial part to help make this clear. Now, we already saw before that we choose the output of the network according to the problem we're trying to solve: regression, binary classification, multi-class classification, and so on. Now we saw that for different outputs we need different loss functions, even though we're always trying to maximize the likelihood or minimize the cross entropy. We end up with different loss functions because the models are different. So we have the loss functions, and now we need to do the optimization. This will be a numerical method. It falls outside the scope of this course to go into detail about the numerical method. So basically, you have the optimizers and it works. But it's useful to have an idea of what the differences are between different optimization algorithms, because then you have to choose them. Always remember the no free lunch theorem. There is no single one that you always use. So you'll have to experiment and understand why things work better in some cases and worse in others. The most basic one is this gradient descent optimizer, and it's simple to understand. It will compute the gradient of the loss function and adjust the parameters for a size, a step of some size in that direction. So that size is the learning rate, is what we multiply to the gradient vector to obtain the update on our parameters, and has a single learning rate for all the parameters, and it just shifts everything in the direction that will minimize the loss function. You can do stochastic gradient descent by presenting the gradient descent optimizer with one random example at a time. So when you present it with an example, it will compute the gradients at that point with the current parameters, and so will shift in one direction. But when you give it another example, it will compute the gradients at a different point, and so shift in a new direction. And if we look at that from the perspective of the space of parameters, it can go in zigzags and change direction depending on the point you're presenting. This is good because it helps avoid getting stuck in some local optimum, because you're always giving different examples, and it can go into different directions until it converges somewhere in a more deeper meaning. It's bad, on the other hand, because it's computationally intensive. Every time you give one parameter, you have to update all. If you give one example, you have to update all the parameters in the network. If they are 20,000 or 200,000 or something like that, then this becomes very slow. So one alternative is to do mini-batch gradient descent, which is also somewhat stochastic, because you take a sample of random examples, a random sample of, say, 100 examples, and then you present that in one go to the gradient descent algorithm. What the algorithm will do is compute the gradients for all these examples with the same set of parameters, so the model is not changing, the network is the same. Add up all those gradient vectors and then give one step in the sum of those directions. This is much faster, especially if you're using GPU, because now you can do this with a matrix operation that can be spread out over different computing, different cores or different GPUs. But as a drawback, that it reduces the randomness in the search for the optimum. So larger batches make things faster, but may make it more likely to get stuck somewhere away from the optimum. Smaller batches take longer time, but may pay off in the end when you get better results. So again, this is another thing that you should experiment. Generally, 64 or 128, something like that, are used. Another drawback is that batches take up memory space, especially if you're using GPU. They must be on the graphics card memory, and if your examples are very large, like images, maybe you have some limitation on the size of the batches because of the memory. Now, one thing that we can improve here is, this happens especially with gradient descent. Suppose that you have a function that is steeper in some dimensions, the loss function, but less steep in others. So you get something like a ravine. When you compute the gradients, it tends to oscillate from one side to the other of the valley because it's always pointing in the steepest direction, and it cannot find that we have a nice path along the less steep direction here. So gradient descent performs poorly there because it tends to zigzag a lot instead of going along the flow of the function. This can be prevented or at least mitigated if we use momentum. The idea of momentum is that we keep adding or averaging the previous gradients, and so those oscillations tend to cancel out, but the other direction that is small at first, but then is always adding up in the same direction, so it starts to gain more speed, more momentum in the right direction. So if you use the momentum optimizer, it will accumulate these information from previous gradients and be more efficient there in those ravines. It still has only one learning rate for all parameters, which is bad because the parameters may, if you have one learning rate for all parameters, those parameters where the gradient is smaller will be updated much slower than those where the gradient is larger. And this may not be very good for training the network. So this is solved by other algorithms like the adaptive gradient optimizer. This uses one learning rate for each parameter, or the ADNE optimizer, the adaptive moment estimation, uses both momentum and different learning rates for all parameters. It has this exponentially decaying average for the previous gradient, so to keep the momentum too. The RMS prop optimizer uses a different approach. It computes a moving average of the squared gradients and then divides the gradient by the square root of that average. So that's why the RMS, it's the root mean square of the previous gradients. What this does basically is that the parameters that have small gradients will get divided by a small value, and so their gradients will effectively work as if they were larger when they're updated. And those with large gradients will have effectively smaller gradients for the update, and it tends to even out the rate of updates overall the network, even though it's not using explicitly different learning rates for everything. So the message here is that you should at least have some idea of how the different optimizers work, because there are situations where some can work better than others. Typically these two may be the most important because ADNE is often used by default because it can be very fast. It can converge faster than the others. However, it has some convergence problems, some instability at the end, and it may work fast in the beginning, but then get stuck and you don't get a good result. RMS prop is very famous because probably It's the most famous optimization algorithm that was never published. This appeared in some lectures by Hinton, and then he never published the paper, but lots of people use this, and it's present in most toolkits. So basically, I would recommend trying these two at least when you're doing experiments, but you can also experiment some of the others. Always remember that it depends on the data. Also, they're very sensitive to the parameters, to the learning rate and so forth, so you should experiment with those. Next week I'm going to talk a bit more about this, how we can look at the loss curves and try to figure out if something's going wrong. But for today you're going to work with this a bit in practice, and then when you have a bit more feeling how to do this in real implementation, we can go back to this analysis. So once we did this, we selected the output, we selected the loss function, we minimize, and now we need to figure out if things are going right for our purpose or not. So this is the one problem here is overfitting. The idea of overfitting is that we are adjusting too much to the data that we have, but then when we want to apply the results to new data, things go wrong because our hypothesis, the instantiation of our model, the values that we chose are too tightly adapted to the data that we have. So there are basically two ways of trying to solve this. We're going to next week look at regularization, which are methods that change the way we train the model in order to reduce this effect. But another thing that we can do is just simply put more neurons or less neurons or more layers or so on and change the model to try to minimize the overfitting. And the problem of overfitting is that things work very well in the training data, but then don't work well at all outside the training data. And we need to monitor that and figure out when this happens so that we can try to prevent it and optimize our hyperparameters, the shape of the model, and things like that. So there are two things basically that we can do. We have a data set. We can set aside one subset for validation. So we train with only part of the data, but we use the rest to monitor things and see how the results, how our network is performing outside the training data. So this would be training and validation. A bit more sophisticated is cross-validation, which we take a data set. So here the data set is represented by this row here. We have red class and blue class. We take this data set and split it into k folds. So in this case it was 5 folds. So we partition the data set into 5 subsets, disjoint subsets. Now we're going to train with 4 of the folds, leave one of the folds out, and we measure the error in the points that were left out. This would be our validation error for this training set. But now we leave another fold out, we train with the remaining 4, and we measure the error there, and we do this 5 times and then average the error. This works better because we are not always using the same points for training and the same points for validation. We get a better estimate because we're averaging the different estimates. So this gives us a better idea of how our model will perform when we train it in that kind of data and then apply it to that kind of data. So cross-validation is actually the standard for most machine learning applications. The problem is that we need to train the model 5 times or k times for k-fold cross-validation. If you have a deep neural network that takes a week to train, this becomes very expensive because now you need 5 weeks just to do the cross-validation. So with neural networks, we have this decision to make. Cross-validation is good, especially when you have smaller data sets, because you're not wasting part of the data just for validation. It gives you a better estimate of the true errors, but you need to do to train your model k times for k-fold cross-validation. Doing training validation works well if you have lots of data. So if you have lots of data, it's not a problem to set a group aside. It's not as good an estimate of how the model would perform when you train it in that kind of data. However, it may be a good estimate of how that particular hypothesis, that particular network will perform, because you're measuring, when in cross-validation, you're averaging over different hypotheses, and in this case, you're just measuring that one. With these networks, you also have to take into account the time it takes to train. In any case, you always need one way of checking for overfitting. Otherwise, you may think you have excellent results, but then nothing works because you trained too much, you adjusted too much to your training data. Then there is one final problem. Let's consider that the true error of the network we produce is the average error over all possible data. So this would be what, on average, the network will perform when it's being used, if it was used for all data in the future. We cannot measure that because we don't have access to all possible data, but we can estimate it. And it's usually useful to have an unbiased estimate of what the true error will be. We cannot use the training set to estimate this because we already fit the data to the training set. So we choose the parameters that minimize our loss function for the training set, and that, of course, makes that training set very biased, or that estimate very biased for the true error. But we also cannot use the validation error if we use that error already to choose the best network, the best parameters, the best activation, and so forth. Because again, we are drawing a sample from some random distribution. We have many different values of the error, and we are choosing the smallest one. And if we choose the smallest one, then it's no longer an unbiased estimate of what the average will be. So one way of solving this, usually, is to reserve a test set, which is a part of our data set that we don't use for any decisions. And we only use it at the end to have an idea, an estimate of what the error will be. This is important because if you're estimating the true error of your final result on data that you already used to minimize something, to choose something, then you get the biased estimate, and it will tend to underestimate the error of your data. Of course, when you estimate with the test set, you may get an underestimation or an overestimation. It's a random sample, but at least it's not biased. On average, it will be the same as the true error. Okay, so let's see the first exercise. We're going to use the modified NIST data set. This is a standard. This is a Drosophila of machine learning, basically. This is a set of images, 28 by 28, from handwritten digits that was modified so that all the digits were centered and the images were all the same size. This is a classical data set for machine learning. What you can do to get this data, you can import this Keras model from TensorFlow and then go into the data sets NIST and load data. What this function does is, if you have the NIST data set on your home folder in Keras samples or something like that, it will just load it. If you don't have it, so the first time you run, it will download it from the server and store it locally. So the first time you run, you'll see a progress bar downloading the data. This is about 14 megabytes or something like that. But afterwards, you can just use it. It's already in the cache. Then this is a set of 70,000 images, which when you load data, you can split into two sets. This is the train and test. This is the train set, the test set. They are also split into two variables, one with the features, which are the actual images, and the other with the labels, which are the integers from 0 to 9, which indicate what is the actual number that was written there, the digit written there. So this way you get 10,000 images for testing at the end, and 60,000 for training. The first thing to do, we're going to use a multi-layer perceptron, and we're going to convert this from the images, which are square, into rows of all the pixel values. So this is the 784 pictures. It's 28 by 28. You can do that with reshaping the matrix. We have more details about this on the PDF file, although I corrected some minor mistakes here in the slides and not the PDF, so look at the slides too, for today. Then we're going to leave aside 10,000 for validation, so we're going to use 50,000 as a training set, 10,000 to monitor whatever changes we're going to do and fine-tuning of the network, and then those 10,000 in the test set will just be used at the end to get an estimate of the true error. You can use the layer function we used last week just to put in your different layers, but remember that at the end you need the last neurons not to have an activation function, so that you can input that output into the softmax cross entropy and to the softmax for the prediction. So remember this part. For the loss function, use the softmax cross entropy inputting the linear part of the neuron, and for the predictions you add the softmax and get the class probability. So another thing that we're going to use today that we didn't use last week, remember that last week we created constants for the data set and then train. But that is not practical when you want to, for example, train with the training set and then use the validation set and the test set and so forth. Also, you cannot do mini batches in that way. So what we're going to do is to use placeholder variables. These are special variables in TensorFlow. In TensorFlow, variables are the parameters that have to be optimized, but placeholders are not optimized. They are not changed by the optimization algorithm. And also, they don't have a fixed size. You can fix their size, but you also can leave it variable. So when you specify the shape of these tensors, you can have a none value in axes that have a variable size. In this case, we're going to give our data as rows of those 784 features, and each row corresponds to one image. So we leave the first dimension with none. This will be filled in by whatever data we put there. The second dimension is the number of columns, is the number of features, so 784. This for the features data, and for the labels, it's just an array of integers with shape none, because the number of values there will depend on the size of the batch we feed into the graph. And now we can create the rest of the graph based on the placeholders, and the thing to do when we run the graph is to specify what data to feed into the placeholders. And for that, you create a dictionary where the keys are these placeholders. So this is the features placeholder and the labels placeholder. These are the keys in the dictionary, and the values associated are the NumPy matrices where you put the data that you want. So I'm assuming here that you all know enough Python to understand this, the dictionaries and so on. If any of you is confused about this, we'll see it in the tutorial, and I'll help out with the Python details. Okay? So you create a dictionary, which is called, when you run the section, this goes into the feed dictionary, feed dict, in the argument of the session run function. You're also going to do this mini batch with random examples. And what I suggest is that you start by creating a NumPy array of indices. So this range goes from 0 to the number of rows there, -1. So these are the indices of the rows. And for each epoch, we shuffle this randomly. So we shuffle the order of these indices. And now we do the mini batch training. We start with the offset at 0, and we select the indices from offset to offset plus batch size. So if batch size is, say, 60, we select the first 60 indexes. We put that into the batch of images for the features. The same thing for the labels. Remember, one alternative would be to shuffle the data itself. But if you shuffle the images and then shuffle the labels, they will no longer match and things will go wrong. Okay? So I'm doing that on the indexes and copying just that slice of each array for these new arrays. Then we create the feeding dictionary and we run optimize. If you want to then check for validation errors, so I'm doing all the batches here until I go beyond the last image, so put in all the batches to train and train at each batch. And then after this, in the epoch, we can ask for the validation error and the training error if you want. But in that case, you can just create the dictionaries with the whole data set, and instead of running the optimizer, because we don't want to change the parameters there, we run, for example, the accuracy operation that we can create here. So how will this work? The first thing to do is we have from our data set labels that are integer values. So some images are 0, so others are 1, and so on. But the output of our network, since this is the multi-classification problem, will be a set of 10 neurons, and we have the probabilities of being 0, 1, and so forth. So we need to one-hot encode our labels. This one-hot encoding is converting a set of values from the initial labels into an array, or in this case an array for each example will be one vector, which has as many elements as the different possible values we have, and has a 1 in the value corresponding to that label and 0 for the others. This in order to match up with what we want the softmax to output. So ideally, for this example, this is not 0, 1, 2, 3, or 4. This is a 5, this digit here. So it has a 1 on the 5, on the position 5, and 0 on all others. And what we want the softmax output to be is 0 probability for all of these and probability 1 for that one. That would be the ideal answer, because it will identify that digit as a 5. So we need to do this one-hot encoding of the labels. We can do that easily here with this one-hot tensor in TensorFlow, where we input the labels. This is a column with all the different labels, and we specify what is the on value and the off value. And this x is -1 is to tell it that the first dimension should be the examples, so the number of labels, and the second dimension, the number of different options that we have. So the depth there. This is the 10, the number of labels that we have. If you use an axis of 0, it will do it the other way. It will have the depth in the first dimension and the different examples in the other. So this depends on how you're setting the tensors, but if you're using the layer function from last week, this should be what you use, because of the way the output will be then at the end. Then what we need is to compute the loss. So the loss can be the average of this cross entropy function. So remember, use this one, or you can use the cross entropy itself, but this just sums everything up. No, sorry, it has to be the average, because otherwise this would be a tensor for all the examples. So you need the mean there. And then you use these the one-hot labels are what outputs from that tensor, and the logits are the output from the last layer. Remember that this is before you have the softmax activation. So these logits are the linear output of the last layer. And this is the loss function that you're going to use on your optimizer. So here you can choose what optimizer you want to use. You're going to also choose the learning rate and minimize that loss function. So this will be the optimizer operation. But there is a different branch here, which is also from the last layer. Oh, sorry, I put their out layer and their last layer, but these are supposed to be the same thing. This is what also enters into the softmax to give you the probabilities of the class. So the reason why we're using softmax here and the softmax cross entropy function there is just because of the numerical stability requirements when we put that into the loss function. But this conceptually should be just the output of this one, and then the cross entropy measured to the actual label. But we can branch the computations here, and this would be for the predictions. The class probabilities are given by the softmax function on the last layer, which is the linear output of those 10 neurons at the end of the network. The prediction will be the maximum of these probabilities. So we're going to take a tensor that has on the first dimension all the examples, and on the second dimension all the class probabilities. The second dimension is axis 1, and we're going to compute the maximum position, or the position of the maximum value along the columns. And this will give us an array with the position where the maximum probability was found. So again, we get this as labels. And now we can compute the mean of the number, or the mean match between the labels and predictions. So we're doing here, this tensor is equal. It gives you a Boolean tensor if for each element of the labels, if it's equal to the prediction or not. We cast this into float because then we need to compute the mean. So use this cast operation here to convert the Boolean into float. And now we compute the mean value. So if 80% of the labels match the prediction, the mean value will be 0.8, and we have the accuracy for this. In this case, we can use the loss function to get an idea of the mean cross-entropy loss function for training or for validation. We'll use the optimizer to do the actual training, but we can use the accuracy operation to measure the accuracy during our run. So you can do this, for example, I would recommend doing this every epoch. So after the while, you can ask for the accuracy on the training set, on the validation set, or the loss functions, whatever you want, and then display those, print them out, or export them to TensorBoard like we did last week. So you can follow the graph. So the goal of this exercise will be to understand these parts, what you're using for optimization, the branching of the computation for the predictions and the optimization, the placeholders, the batches that you're going to generate, understand how these things are working, and then experiment with it. So try different activation functions in the hidden layers, regularize linear units, sigmoid, and so forth, and see how things work. Try different dimensions for the network, different layers, different number of neurons, and also different optimizers to check how the gradient descent is going. So we're going to next week look a bit more in detail into how we can interpret those graphs, but for this first approach, just take a look and experiment a bit. Remember this, check your overfitting with the validation data. So if you see the accuracy on the validation decreasing as the accuracy on the training set is increasing, this shows that you're training too much on the training data and losing accuracy outside. And in the end, you can just train everything with a complete training set, evaluate the performance, and take a look at the performance of the best classifiers here. There is a table there in the side. Okay, exercise 2 is mostly the same thing, so basically the construction will be very similar, but it's a smaller data set. You're going to try to predict the miles per gallon, the fuel consumption of cars based on several indicators. And some differences here, you should shuffle the data because the missed data is already shuffled, but this one is not. The target value is on the first column, and the features are the remaining column. We only have 392 examples, so use 300 for training and 92 for validation. Or if you want, you can keep those 92 for testing and use cross-validation. However, this is optional because it depends on the computer that you're using, and you should not take too long running this during the tutorial because then it's a waste of time. You need a linear output for the last neuron and use the mean square error function for training. There are some typos here, I don't know why. Try also different optimizers and so on. But the general scheme of the placeholders, the batches, and things like that, it's the same as the one before, so you can use the same code. This is just a different example with fewer training data and also with the linear regression, with the regression instead of the classification problem. So you need to change the way the loss functions and so forth. So to sum up, we saw this idea of maximum likelihood or cross entropy in general, but then how this translates into different loss functions. Very important, the idea of overfitting. So those of you who did machine learning probably already know this by heart, but if you don't have experience with machine learning, this is a very big problem, so you need to take special attention that you don't train too much, and then it only performs well on the training set and cannot generalize. And these exercises. So I recommend reading chapter 6, also the beginning of chapter 8, but note that the book goes into much greater detail on the formalities of all these elements. We're not going to require that level of detail. The level of detail that you need to understand is basically the slides and the lecture notes, okay? So questions?